All right, let's talk about a couple other relationships. We've seen Boyle, pressure, volume; Charles, volume, temperature; Avogadro, volume and moles. Let's look at some other relationships as well. In this one, we're going to talk about relationships actually between all of the factors of a gas, something called the combined gas law. And then we'll look at something also called the ideal gas law. I know that's quite a few laws to keep in mind, but hopefully through using some strategies we've seen in previous Scribblecasts and ones I'll show you here, you'll be able to identify which law you need to use. Okay, so the combined gas law relates the volume, pressure, and temperature of a gas that's being changed. So if I have a gas at a certain pressure, volume, and temperature, if I were to change any one or all of those, I could determine one of them which I would keep unknown. Notice that in here, the moles of the gas is constant. So we're not changing the number of moles. But this is one like, well, let's try a question. So I have a sample of hydrogen gas at 63 Celsius. So that's what it's starting at. So temperature 63 plus 273. So 63, so 0.15 would be a 6, a 13, and a 3. So the initial temperature is 336.15 Kelvin. Notice we always change those to Kelvin. With a pressure with a volume of 3.65 liters and a pressure of 4.55 atmospheres. The pressure is changed to 2.75 atmospheres, and the gas is cooled to minus 35. Oh, great. So now I have to go 273.15 and subtract 35. So that'll be 0.15. You can see my adding abilities here, or subtracting abilities. So 238.15 is the new temperature. Calculate the new volume. They want to know that. Notice that the moles didn't change, so I won't use those. So here's a question where since the temperature changed, since the pressure changed, I'm going to have to use the combined gas law. You know, I wonder if somebody came up with that. All the other ones, they got a name. Maybe I should claim this one. I'll call it the Hamilton gas law. Well, maybe not. Anyway, combined gas law is its name. So I would use this formula. Like we've done before, probably I would solve the formula for what I'm looking for. So V2, I need to solve for V2. So again, using our formula manipulation, that'd be P1 V1 T2 over T1 P2. Let me think about that for a second. Yeah, that's right. So again, if you have troubles with that, holler. So V2 is equal to pressure 1, 4.55 atmospheres, times V1, 3.65 liters, times T2, 238.15 Kelvin, over T1, 336.15 Kelvin, times P2, 2.75 atmospheres. Notice how nice this is to have when you're doing a question. Just sort of fill in those blanks, and then you just plug them into the right spot in the formula. Really, the hardest part of doing any question like this is manipulating your formula. So that would be one thing I would practice and make sure you're very good at. Okay, so now I have to take my calculator, trusty calculator, and go 4.55 times 3.65 times 238.15, and then I have to divide that by 336.15, and I have to divide it by 2.75 equals. Okay, so my new volume, and I probably should have guessed at it, but it was tough because I had two things changing. So the pressure that went down, so I think maybe volume would go down, but the temperature went down. So again, the volume, when I was doing this, it would be sort of hard to figure out exactly, or to guesstimate what it would be. So V2I came up with 4.27847, etc. Kelvins cancel, atmospheres cancel, so my unit is liters. So volume 2, rounding to the appropriate number sig figs, I have 3 here, 3, 3. The temperature, when I added it with Kelvin, came out so that I had 5 sig figs in each of those. So it looks like 3 is what I need. 4.28 liters would be the final volume. Okay, so that's using this new law called called the combined gas law. And you use that if you have a gas at a certain volume, pressure, and temperature, and you change two of those things. I guess if you don't change two things, then you could use either Boyle or Charles's law. But if you change two of those conditions, then you can use this combined gas law. Now, all the laws that we've looked at so far have been laws where I've done changes to the gas. So I've changed the volume, or I've changed the pressure, or changed the temperature, or changed how many moles of gas. There's another law that's really quite useful. I don't know if it's a law, but I guess we call it the ideal gas law. But it is used when I don't change anything. All I want to know is some characteristics about a certain gas. Okay, so last formula for a while. So we've looked at Boyle and Charles, Avogadro, and the combined. Those are when things change in the gas. But what happens if I maybe know the pressure and the volume of a gas? I know how much gas I have, but I'm, let's say, looking for what the temperature is. So I'm not changing anything in the conditions of the gas. All I'm doing is I'm wanting to find out one of those conditions given a bunch of the other ones. To do this, I can use this thing here that's called the ideal gas law. So PV equals nRT. So, for example, I'll get to an example in a second. I sort of skipped over this letter right here, R. And R stands for the universal gas constant. And for our purposes, we like using kilopascals, and so we use this value of R. There's actually a number of different R values, but it depends on what units they're using. For us, we're using universal gas constant as 8.314 liter times kilopascals over Kelvin mole. That's probably the most number of units you've seen behind a number. But it's a constant, and we can use it for ideal gases. If we're given 3 of the 4 conditions of the gas, we can solve using this universal gas constant for the final condition. So let's try a question. 2.5 mole sample of nitrogen gas has a volume of 5.5 at a temperature of 27. The question says calculate the pressure of the nitrogen gas. Notice there's no change in the conditions. If there was a change in conditions, got to use Charles, Boyle, combined, Avogadro, one of those guys. But here there's no change. All they're doing is they're giving me number of moles, so that's down here, 2.50 moles. They're giving me a volume of 5.50 liters. They're giving me a temperature of 27. Hopefully you're automatically thinking now when they give you a temperature to change that immediately to Kelvin. So my temperature is 300.15 Kelvin. Calculate the pressure. So here they want to know what the pressure is. Notice that I have nothing over on this side. So if I have no changes to the gas, I don't need those, that should give me an idea that what I'm going to be using is the ideal gas law to solve for the unknown property. If they give me a question like this and there's two unknowns, and I don't have anything over on the other side, I'm pretty well stuck. I won't be able to determine any of those. I need to have all but one of those values. Okay, so they're looking for pressure. Let's solve this equation for pressure. P is equal to nRT over V. Notice that in all these times that I've been switching these, if I'm looking for P, I want to get rid of V, so I'll divide both sides by V. On this side, the V's cancel, and over on the other side, the V stays. Hopefully that helps you a little bit if you're doing these. Okay, so pressure is equal to number of moles, 2.50 moles, times the universal gas constant. We said it was 8.314. What were the units again? Liter kilopascals. Liter times kilopascal over Kelvin mole. I like writing those units in just to make sure when I cancel things that things get canceled properly. Especially like with pressure, sometimes I'll give you pressure in atmosphere. If I'm using kilopascal, or this R value I'm using this as my R value, I have to have my pressure in kilopascal. Right in the units sort of helps me tweak on that. Okay, times the temperature, 300.15 Kelvin, divided by a volume of 5.50 liters. So if I do my canceling, moles cancel, kelvins cancel, liters cancel, and so the units that I'm left with are kilopascals, and that's a pressure, so that makes sense. Okay, so pressure then is equal to, now I bring out the trusty calculator. Okay, so 2.5 times 8.314 times 300.15 divided by 5.5 equals. Alright, so I'm coming up with a fairly big number. Does that make sense? Yeah, that's probably about right. Okay, so 1,134.29414, that's kilopascals. Now, originally I have 3 sig figs. I've got to change this to 3 sig figs, so I can write it as 1, 1, 3. That's all the sig figs I can get. This one is less than 5, so I'll leave it as 0. So 1,130 kilopascals. As well, I could have written that in scientific notation, so 1.13 times 10 to the third kilopascals. Now, using your calculator, if you're not coming up with this number, I would make sure that you learn how to use your calculator, whether it's using brackets or what you do. Make sure that you learn how to use your calculator so you can come up with that number every time. Lots and lots of students, the issues that they have in this section are first manipulating formulas. Make sure you're good at that. And secondly, just using your calculator. A lot of people can maybe manipulate, but then once they get the numbers there, they're not sure how to put them in your calculator. Make sure you're comfortable with both of those steps. Okay, so that is our combined gas law, henceforth known as Hamilton's combined gas law, and the ideal gas law. This one is similar to Boyle, Charles, and Avogadro, where there's a change in the conditions of a gas. I can use that. This one here is where I need to identify one of the unknown conditions of the gas.